Okay class. Our next topic is Gauss Theorem. Before to study this Gauss Theorem, we have to study about the area vector. Area vector is a hypothetical concept where we have to give the orientation to area. Orientation means direction. Here we give for an area, draw the unit vector. This is area element ds. Then area vector is a vector perpendicular to the surface and outward. And it is a hypothetical concept. Every time we consider it perpendicular and outward the surface. Perpendicular and outward the surface. Next we have electric flux. That is number of electric field lines passing through the surface normally is called the electric flux, and it is a scalar quantity denoted by phi. Now, how this phi is written as mathematically? If we have this surface and these are the electric field lines, and we consider a small element, electric field lines, and area vector ds vector at angle theta. Now we consider that number of field lines passing through the surface normally. So we are considering the component of electric vector which is normal to this surface, and area vector is always normal to the surface. So the component along area vector is considered as normal, and here it is E cos theta. So how we write the electric flux? That is E cos theta into vector, area vector. Then this is E dot ds called d phi, and for whole surface it is considered as surface integral of electric field, that is called the electric flux. That is surface integral of electric field. Now, what is the Gauss theorem? Gauss theorem is for a closed surface, the electric flux. For a closed surface, the total electric flux phi is 1 by epsilon naught times the total charge enclosed in that surface. 1 by epsilon naught, the total charge enclosed in that surface is called the Gauss theorem. And what we define for the this electric flux, that is the surface integral of electric field. It means Gauss theorem can be stated as surface integral of electric field is Q by epsilon naught. This is the another statement for this. Now how we prove this Gauss theorem? And it is always proved for the spherical symmetric closed surface. And for its proof, we have considered a spherical surface with center O and radius point is R plus Q charge. This is our observation point. Here the electric field is E, and if we consider the area vector around it, this is ds vector. Now for the point charge, electric field is 1 over 4 pi epsilon naught Q upon R square R cap, and for small electric flux, E dot ds vector, that is 1 by 4 pi epsilon naught Q R R cap ds vector. R cap unit vector, both are in same direction. So d phi 1 over 4 pi epsilon naught ds cos 0, and cos 0 is 1. So how we consider phi? 1 over 4 pi epsilon naught r square for the closed surface. This is the surface integral, and its value is 4 pi r square. So phi 1 over 4 pi epsilon naught Q upon r square 4 pi r square. What we got here? Flux is Q by epsilon naught, and this is the Gauss theorem. and the surface which enclose no charge, then its flux is 0. And for dipole, where we have the positive and negative charge, the total charge is 0, then the flux is 0 for the dipole. Gaussian surface. There we have a term, Gaussian surface. Gaussian surface is a surface around the charge distribution. We have a 4 type of charge distribution, that is point charge distribution, linear charge distribution, surface charge distribution, and the volume charge distribution. And Gaussian surface is an imaginary surface around the charge distribution to apply the Gauss theorem. Now we have some applications for the Gauss theorem. Applications. First is how we derive the Coulomb's law by using this Gauss theorem, Coulomb's law. Here we have the two charges Q1, Q2 at a distance r. Let me say Q2 is present in the field of Q1. So present in the field of Q1. So force on Q2 due to the field of Q1 is Q2E. This is the one. Now to apply the Gauss theorem, we have to apply the Gaussian surface. So we draw the surrounding surface, that is considered as Gaussian surface. And around this again we consider small area vector, that is ds vector. Now according to the Gauss theorem, the surface integral E dot ds vector is Q1 upon epsilon naught. And now they both are in same direction. So this is E ds cos 0 Q1 epsilon naught. And here E ds Q1 epsilon naught. What we got? E into 4 pi r square Q1 epsilon naught. This is 1 over 4 pi epsilon naught Q1 upon r square. Now we use this value in this equation. What we got here? 1 by 4 pi epsilon naught Q1 Q2 upon r square, and that is called the Coulomb's law. This is the Coulomb's law by using this Gauss theorem. Okay. And the next is electric field due to the line charge by using this Gauss theorem. Line charge distribution, electric field is, we have this line charge distribution, and by using this we have the observation point P at distance r. So to calculate the electric field due to this charge distribution at point P, we draw the Gaussian surface. Here the Gaussian surface is in the form of cylinder. L be the length of cylinder, r is the radius, this is the electric field, and here we have the area vector around that point P. But in this case, the flux is contributed only by the curved surface, because if we draw the Gaussian surface, if we draw the area vector here, it must be outside and perpendicular, and electric field is this. If there is a change of direction of electric field, then it is not uniform, it is not treated as a Gaussian surface. So here it is 90 degree, and if we draw here the area vector and electric field, it is again 90 degree. So only contribution is around the curved surface, and area is 2 pi r L. And according to the Gauss theorem, flux is charge upon epsilon naught. What about the charge here? Lambda is the charge density. So E into 2 pi r L lambda L epsilon naught. What we got here? 1 upon 2 pi epsilon naught lambda upon r. This is the electric field at a point due to the line charge distribution, and if we draw the graph between E and R, it must be a curved line for this variation. So this is the electric field due to a line charge distribution, second application. And the third is due to the infinite plane sheet of charge. Now the electric field due to the infinite plain sheet of charge by using the Gauss theorem. We have this plain sheet, positive charge. Due to this charge, we have this point observation P, where we have to calculate the total electric field. And for that, we again draw the cylindrical Gaussian surface across this point. Now here, the electric field contribute only end to end, not on the curved portion. Again, the same. If we apply here the area vector, they are parallel. But if we apply at the curved surface area vector, that will become perpendicular to the electric field. So here, what should be the total flux here? Electric field into two end sides area A. If A is the area of these end sides. And according to Gauss theorem, this is sigma A, because this is the surface charge density. So what we write here, E into 2A sigma A upon epsilon naught, cancel. So when it is a plane sheet, what will be the charge, electric field due to the charge on plane sheet is sigma upon 2 epsilon naught. And one point that has to be clear here, that this electric field is not depend upon the distance. So if we have a graph for this E and R graph, it will be a straight line which show the independence of this. And if this plate is a conducting plate, this is an infinite plane sheet, and if it is a metal conducting plate, then what we got here? Then here we consider the charge for 2 times 2A upon epsilon naught, and our answer become this sigma 2A upon epsilon naught, that is sigma upon epsilon naught, and this is the electric field by the conducting plate. Okay, and if we place these two infinite plane sheet or conducting plate parallel, then how we calculate the electric field here? If the two sheets are placed parallel to each other, two plane sheets A, B, which have the charge this one, sigma A, sigma B. Now, when the two plates are placed parallel, the region is divided into three parts. And in one region, what is the electric field? If we considering the sign conventions, away, this is the positive, away from this sheets, the field is positive, and towards the left, the sheet is electric field is negative. So in one region, both are negative. 2 epsilon naught, 2 epsilon naught. So it is minus 1 upon 2 epsilon naught sigma A, sigma B. And in second region, what is electric field? For two first, they are here. And in second, it is this side, it is this side. Means this is positive and this is negative. And in third, both are considering in positive direction. So 2 epsilon naught sigma A, sigma B. Both are positive. And if the sheet is considered as sigma A is plus sigma, sigma B is minus sigma, then it becomes 0. It becomes 0. The only field is exist between the two plates, and it becomes sigma minus sigma 2 sigma upon 2 epsilon naught, that is sigma upon epsilon naught. Means if we have the two sheets, give them equal and opposite charge density, then the electric field is only consist in between the plates, and that is equal to sigma upon epsilon naught. And this can be do for the conducting plates also by taking their electric fields and by taking the value of them. Okay. And the next application is spherical shell. The electric field at a point outside the shell, on the shell, and inside the shell. How we calculate the electric field? So we consider a shell. Center O, radius r. The charge is outside. Obviously, the charge is placed outside the shell. So our first observation point is here at distance r, where this r is more than radius. So we again draw the Gaussian surface around this. Here P point, electric field, area vector around this point. Then what we have? We have again the flux that is equal to total EDS, means E into ds or E into 4 pi r square. And what about the Gauss theorem? Gauss theorem is Q upon epsilon naught, because the Gaussian surface encloses this charge. Then what is the electric field outside the spherical shell? That is 1 over 4 pi epsilon naught Q upon r square, that is outside the spherical shell. And if it is on the spherical shell, this point is at on the shell at this point, then what should be the electric field? 4 pi epsilon naught Q upon r square. This r more than r, this is equal to r. And if the point lies inside the shell, if we consider this is the shell O point. Now here we have the observation point P and R, charge is outside. Here the R is less than R. Then what about the electric field? It becomes 0, because the charge remain outside the Gaussian surface, and Gaussian surface encloses 0 charge. It means there is a no electric field inside this spherical shell. Okay, clear? And if we considering the solid sphere, to find out, to calculate this electric field. In the solid sphere, the first case is similar. The charge is distributed and we considering the point outside, taking the Gaussian surface, taking this, and the value got this. And on the surface, again the value is the same when the r is equal to the radius of this sphere. Now the third point, where we have in the third point, the electric field is not 0 like the case of this spherical shell, because in third point here the sphere is a solid, and when we considering this observation point radius r and this is capital R, the charge is redistributed it, because it is a volume charge density in this case, volume charge density. And what about the electric field? E into 4 pi r square Q dash upon epsilon naught. And what's the value of this Q dash? How we considering this Q dash? This Q dash is taken as Q dash is equal to Q upon 4 by 3 pi r cube into 4 by 3 pi r cube. And what we got here in the Q dash, that is Q r cube upon r cube. And when we put this value here, what we got the electric field? 1 over 4 pi epsilon naught, then Q r cube upon r square r cube. And we get here the value, this 1 by 4 pi epsilon naught Q r upon r cube. This is the electric field for the solid sphere when it lie inside the sphere. Now if we draw the graph for both shell and sphere for the variation of this electric field, then what we have the graph for the shell. This graph is in this shape. This is electric field, this is R, this is inside the sphere. But when we considering it for the solid sphere, then the graph here it is okay. But in this last point, when we write this electric field 1 by 4 pi epsilon naught, and it become QR upon R cube. This R distance of point. Here the graph distance, that is directly proportional, and this will be show the maximum electric field that will be at the radius of the spherical shell or spherical surface. Okay. Thank you.